Hello everyone, welcome to Pre-Calculus sections 4.1 through 4.2, Graphs of Rational Functions, Part 1. Rational functions are functions that have a numerator and a denominator where the numerator and the denominator can both contain a variable. So the main ideas that we're going to discuss in this video are vertical asymptotes, holes, horizontal asymptotes, domain restrictions, x-intercepts, y-intercepts, and how to graph rational functions. First, let's talk about vertical asymptotes. So looking at this example over here, f of x is this rational function. Here's your numerator and here's your denominator. The first thing you want to do is factor any polynomial that can be factored. X plus 2 is fine, but you can factor x squared plus x minus 12 into x minus 3 times x plus 4. So our factoring skills come into play quite a bit when we're dealing with rational functions. Next, we want to identify the x values that cause the denominator to go to 0. So to do that, you want to look at these two factors here. So when x is equal to 3, x minus 3, that factor is 0. And when x is equal to minus 4, x plus 4, that factor goes to 0. So it's the x is equal to whatever those values are, which cause 0 in the denominator. Those are called your domain restrictions. So we want to take those two numbers out of our domain. So we're going to say x cannot equal to 3 and x cannot equal negative 4. Okay, those are domain restrictions. Vertical asymptotes are equations of vertical lines. Those equations, x equals to a number, occur at the identified places where you have domain restrictions. So vertical asymptotes are another way of saying you have a domain restriction at that x value. So the equation of the vertical line for the domain restriction x can't be 3 is the vertical line x is equal to 3. And for the negative 4 domain restriction, the vertical line x is equal to negative 4. That's the equations, those are the equations of the vertical asymptotes. Vertical lines, these are. So when we get to graphing rational functions, the graph of the rational function you will see will split at the vertical asymptotes here. These two vertical lines, we're going to have a split of the graph. We'll get into that later. When you're graphing a rational function, you graph the vertical asymptotes as dotted vertical lines through these x values. Next, we'll talk about x-intercepts, also called zeros, of a rational function. We know something about zeros already. We know that those are the solutions to the equation f of x equals 0. So if we have this rational function right here, we want to find out what causes f of x to be 0. So the way that you tell is you look at your numerator. If either of these factors equals 0, then f of x will equal 0. 0 divided by any number is always 0. So for the first factor, x minus 2 to equal 0, x would be 2. And for the second factor, x plus 5 to equal 0, x would equal negative 5. So we say x is equal to 2 and x is equal to negative 5 are the zeros of the function f of x, and the points 2, 0 and negative 5, 0 are the x-intercepts of f of x. Next, we're going to talk about holes. Holes are also called point discontinuities or removable discontinuities in a rational function. A hole exists when the numerator and the denominator have a shared factor, the same factor. Like in this example here, we have an x minus 2 in the numerator and in the denominator. We worked with these a little in Algebra 2 when we would cancel these two factors out to simplify the rational expression. When we're talking about graphing functions that have matching factors in the top and the bottom, we still cancel them out, but we retain the knowledge that we have a whole for graphing purposes. And also in calculus, we talk about discontinuities more. So what's going on? We're saying that there is an x value, some value a, which causes the function evaluated a to have 0 on the top and 0 on the bottom. Okay, so we said the factors will cancel, but x is equal to a is undefined in the original function. So we can't lose sight of the fact that x is equal to a is not in the domain. All right, so we take it out of the domain. It's a domain restriction. In this case, x is equal to 2 is a domain restriction. So matching factors, there's a whole. X is equal to whatever that value is here. In this case, 2 is a domain restriction. So x cannot be 2. When we get to graphing these rational functions, we'll see that we draw the whole as an open circle. So we evaluate this part of it, in this case x plus 3 over x minus 3 at 2 to give us the point 2 comma whatever it is. That will be an open circle on the rest of the graph. Now let me point out that if you graph this function on a graphing calculator, it would not give you an open circle at the whole. That's because the graphing calculator cancels the factors before going ahead and calculating the points. So if you're using a graphing calculator for any reason, and like I said, we're doing these things analytically, so we shouldn't be using our graphing calculator for learning how to do these analytically, you wouldn't see a hole there in the graph. Let's do a couple of examples to review what we just learned about vertical asymptotes, domain restrictions, holes, and x-intercepts. So looking at number 1, we're going to look at let's find the vertical asymptotes first. So we're going to look at the denominator to find our vertical asymptotes. So you set x minus 4 is equal to 0, and you can see that x is equal to 4 is going to cause your denominator to go to 0. So that tells us my vertical asymptote is the equation x is equal to 4. So if we're talking about domain restrictions, x cannot be equal to 4 because it causes an undefined situation. So we can say that our domain is all real numbers except x cannot equal 4. Next, let's look for holes. We're trying to see if we have any factors that are matching top to bottom. So there's no holes in number 1. Now the x-intercepts. For the x-intercepts, we're looking at the numerator, which x values cause the numerator to go to 0, which means the whole value of the function would go to 0, f of x is equal to 0. So we can see that a 3 here and a negative 5 here would cause your numerator to go to 0. So my x-intercepts are the points 3, 0, and negative 5, 0. Let's look at number 2. So for the vertical asymptotes, I look at the denominator, and I find the x values that cause either of these two factors to go to 0. So 2 for this factor and 3 for this factor. So my vertical asymptotes are the equations x is equal to 2 and x is equal to 3. So there's 2 vertical asymptotes. Now for the domain. So we have domain restrictions for 2 and 3. X cannot be 2 and x cannot be 3. So the domain is all real numbers except x cannot be 2 or 3. Next, we'll look for the holes. So we want to see if there's any matching factors, top and bottom. So this is a no, no, no. So there's no holes in number 2. So now for the x-intercepts. the x-intercepts, we look at the numerator to find out the x values that cause the numerator to go to 0. So if x is 1 or x is negative 5, we're going to get 0 for the factors in the numerator, which would cause the function f of x to take on 0. F of x equals 0. So our x-intercepts are the point 1, 0 and the point negative 5, 0. For example 3, first we'll do the vertical asymptotes. So we're going to notice, though, right off the bat that we have a matching factor here. Now, before we figure out the vertical asymptotes, we want to make sure we understand whether or not there's a hole. Because if the x value causes a hole, then you won't say that it's a vertical asymptote. It's going to be one or the other. All right, so let's do the holes first in this one here. So we could see that we have a hole when x is equal to 8. All right, so if those factors are going to cancel out, then they won't show up in the graph. The only thing that'll show up having to do with that hole will be your empty circle at the value, at the ordered pair hole, at the ordered pair 8, comma, f of 8. All right, let's just go ahead and figure out what that is now. So I would be putting 8 in, let's find f of 8. I'll write it up here. F of 8 would be 3 times 8 plus 5, and 2 times 8 minus 3. So that's 24 plus 5, 29. 16 minus 3 is 13. So my hole is going to be plotted as an open circle at 8, comma, 29 over 13. We would have to get a decimal value for 29 over 13. Okay, so that's your hole. All right, so we did the hole already. All right, now let's do the vertical asymptote. Since x is equal to 8 is a hole, it cannot be a vertical asymptote. So let's look at this factor here in the denominator. What value causes this factor to go to 0? So 2x minus 3, I'm going to solve that for x. So that means 2x is equal to 3. So that means x is equal to 3 halves is going to be a vertical asymptote, because when x is equal to 3 halves, the factor 2x minus 3 goes to 0. All right, so I write it as an equation of the vertical line, so x is equal to 3 halves. So we would say for our domain, all real numbers except x cannot be 3 halves because it causes a 0 in the denominator. Okay, so the last thing is the x-intercepts. So we look at the numerator for the x-intercepts. So when x is equal to negative 5/3, the factor 3x plus 5 in the numerator would go to 0. So my x-intercept, I have one of them, would be the point x is equal to negative 5/3, y is equal to 0. Looking at problem number 4, you can see that we're going to have to factor before we can clearly see the answers to our questions that we're asking ourselves. So let's go ahead and factor. And it's worth reviewing the factoring, since some of us are still a little hesitant about factoring with a leading coefficient that's non-1. So let's factor 3x squared plus 7x minus 20. So I've got 3 times negative 20 is negative 60. 1 times 60, 2 times 30, 3 times 20, 4 times 15, 5 times, 12, 6 times 10. Okay, so there's a lot of ways to multiply to get 60. So we need 2 ways that add to give me positive 7 and multiply to give me negative 60. So I can see if I add 5 and negative 12, negative 5 and 12, I'm going to get positive 7. And if I multiply negative 5 times 12, I'm going to get negative 60. So I'm going to use those two numbers in the middle. Instead of plus 7x, I'm going to have minus 5x plus 12x minus 20. So then I'm going to factor it by parts. So I find a GCF of the first two terms, so that would be x, and then I'll be left with 3x minus 5. I'll bring down my plus, and then I find the GCF of 12 and 20, so that would be 4. So that would be the same factor over here, 3x minus 5. So my final factored form would be 3x minus 5 times x plus 4. Okay, so I wrote that in the numerator. Now we got to factor the denominator. Now I can't stress enough that factoring is a very, very important skill that you must understand at this level, especially if you're planning on going any further, let's say to calculus. So you might take some extra time to practice some factoring problems, or ask me for some extra factoring problems if you're feeling weak on this. So I'm factoring 2x squared minus 13x plus 15. So I've got 2 times 15, that would be 30. 1 times 30, 2 times 15, and 3 times 10, 5 times 6. So those are my possibilities. So I have to multiply to give positive 30, and I have to add to give negative 13. Well, you have to have two negatives if you're going to add to get a negative number and multiply to get a positive number. So you can see that they're going to go here. So I have negative 3 minus 10 is negative 13. So now you're going to replace your middle term with those two terms. Because I have a leading coefficient, I have to factor by parts. All right, now I'm going to cut it in half. GCF of the first two terms is x, so I'm going to take that x out of both of those terms. Bring down your minus. Factor the GCF out of the second two terms. And you should get this same factor right here if you're doing it correctly. So now my final factored form would be 2x minus 3 times x minus 5. Let's write that down here. 2x minus 3 times x minus 5. So this is your starting point. Okay, so from here, let's see if we have any holes. No matching factors, so there's no holes. So we don't have any holes. So let's do the vertical asymptotes next. So my vertical asymptotes are going to occur where my denominator factors go to 0. So this one's going to occur at positive 3/2. This one at 5. So our vertical asymptotes are x is equal to 3/2, x is equal to 5. Okay, so the next thing would be our domain restrictions. So our domain is all real numbers, except x cannot be 3/2 and it cannot be 5. Now for the x-intercepts, we look at the numerator. And so for this factor here, x cannot be 5/3. 5/3 is an x-intercept. For this factor here, negative 4 is an x-intercept. All right, so I'm going to write those as points. So I have 5/3, 0, and I have negative 4, 0. Those are my x-intercepts. All right, let's look at the last one, number 5 here. So I'm going to factor the numerator and the denominator and then examine what I have. So I've got 2 times 15 is 30. 1 times 30, 2 times 15, 3 times 10, and 5 times 6. And I have to add to get 11, my middle term. So 5 and 6. So that's 2x squared plus 5x plus 6x plus 15. And then I'm going to cut it before the sign. Factor out an x out of the two terms, the first two terms. Bring down my plus, factor of 3. So I should get the same factor, 2x plus 5. So factored form, 2x plus 5, x plus 3. Okay, so for the denominator, I have 3 times negative 12 is negative 36. 1, 36, 2, 18, 3, 12, 4, 9, 6, 6. I have to multiply to give a negative 36 and add to get a positive 5. So that must be negative 4 and 9. So replacing the middle term with negative 4x plus 9x and factoring by parts, I've got x times 3x minus 4, bring down the plus, factor out of 3, should have the same 3x minus 4 factor. So I've got 3x minus 4 times x plus 3. So I'm going to write that up here. 3x minus 4 x plus 3. Okay, so this is our starting point. So now we want to examine it and see if there are any holes. So holes occur when you've got a matching factor on the top and the bottom that we cancel. So it looks like we have a hole here. Those are the same factor. So we're going to have a hole when x is equal to negative 3. Negative 3 is going to cause a 0 over 0 situation for f of x. All right, so I'm going to say I have a hole at x is equal to negative 3. So I'm going to have an open circle at the point negative 3, f of negative 3. So f of negative 3 I could figure out by plugging negative 3 in to the remaining two factors and getting that value. So if I go ahead and do that, I can just show you how we would figure out where our open circle is going to be. So that's negative 6 plus 5 divided by negative 9 minus 14. So let's just go ahead and say f of negative 3 is going to be 1 over 13. So it's a small value. All right, so I'm going to have an empty circle there at that point on my graph. Negative 3 for your x value, 1 over 13 for your y value. Okay, next we're going to find our vertical asymptotes. So our vertical asymptotes occur where you've got a 0 in the denominator. All right, so we've got one more factor to examine. Remember, if your x plus 3 causes a hole, it cannot be also a vertical asymptote. Be one or the other. So check your holes first. All right, so now if x is 4/3, then you're going to get a 0 for that factor. So you're going to have a vertical asymptote at x is equal to 4/3. So the domain will be then all real numbers, except x cannot be 4/3 because it causes a 0 in the denominator. Okay, so the last thing is our x-intercepts, which we get from the numerator. Once again, the whole is now canceled, so the other factor is going to give you your x-intercept here. So x is equal to negative 5/2 will cause that factor to go to 0, so you have an x-intercept at the point negative 5/2, 0. Next, we're going to talk about horizontal asymptotes. So we use 3 rules to find the horizontal asymptotes. Now this is also something we learned in Algebra 2, but we're going to do it again here in pre-calculus. So horizontal asymptotes are determined by the highest power term in both the numerator and the denominator. So the highest in the numerator and the highest in the denominator, we need to know both. So then we say that the horizontal asymptotes describe the end behavior on the left and the right ends. there will only be at most one horizontal asymptote. So the same end behavior occurs on the left and the right because there is only one horizontal asymptote. When we start graphing these things, it'll be clearer what we're talking about here. So it doesn't describe the middle behavior close to the vertical axis. It describes the behavior of the rational function way out toward negative infinity and way out toward positive infinity. Horizontal asymptotes have y equations. Vertical asymptotes had x equations because they're vertical lines. Horizontal asymptotes have y equations because they're horizontal lines. Horizontal asymptotes are graphed as dotted horizontal lines. Y is equal to whatever the number is. So here are the rules for finding horizontal asymptotes. The first thing you want to do is multiply out your factors so that you have it in polynomial over polynomial form. Okay, so that way it's easier to look at your highest power. For case 1, if the lower power is in the numerator and the higher power is in the denominator, then the equation of your horizontal asymptote is y is equal to 0. For case 2, if the higher power is in the numerator and the lower power is in the denominator, then you will not have a horizontal asymptote. For case 3, if the powers are the same in the numerator and the denominator, then you will have a horizontal asymptote of the form y is equal to the ratio of the leading coefficients. All right, now something that we're probably not going to have time to get into in this course because of our time restrictions. For case 2, when the degree of the numerator is 1 higher than the degree of the denominator, you will actually have a slant asymptote. All right, so like I said, we're not probably going to have time to get to that. And that the slant asymptotes we find by dividing the denominator into the numerator and looking at the result there. So polynomial long division is employed to find the equation of a slant asymptote. So please make sure that you've written these 3 rules down in your notebook. You'll need to look at those when you have quizzes and tests and homework problems that have horizontal asymptotes. So stop this video at any time, pause it, and make sure that you're writing down all of these things that I'm telling you here. All right, we're going to find the horizontal asymptotes. So you look at the powers of the numerator and the denominator after multiplying out your factors. So I've got x squared plus 5x minus 3x minus 15 over x minus 4, which is x squared plus 2x minus 15 over x minus 4. Okay, so now I'm going to look at the powers of the highest terms here. So I've got a 2 on the top and on the a 1 on the bottom. So the degree of the numerator is higher than the degree of the denominator. So I go back to this page and I see that that's this case 2 here. So none. There's no horizontal asymptote, but there might be a slant asymptote, and we're not going to talk about that yet. Okay, we're looking at number 2. So we're going to rewrite it as x minus 1 divided by x squared minus 3x minus 2x plus 6. Well, we can go ahead and just look now without finishing that work and see that the degree of the numerator is less than the degree of the denominator. So that's case 1, lower on the top, higher on the bottom. So I'm going to say my horizontal asymptote is y is equal to 0. All right, the third case, if you multiply this out, you're going to get x squared plus 5x minus 2x minus 10. and then I'm going to get 2x squared minus 3x minus 16x plus 24. All right, I don't really care about any of the lower order terms when I'm using my horizontal asymptote rules. I only care about my highest order terms. So I'm just going to circle those. All right, now let's look and see which case we have. So I've got the case where they have the same power on the top and the bottom. So my horizontal asymptote is going to be the ratio of the leading coefficients. So x squared and x squared are the same. So my leading coefficient on the top is 1. On the bottom is 2. So my horizontal asymptote is going to be y is equal to 1 over 2, 1/2. All right, number 4, I've got it already multiplied out, so I can just go ahead and look at those two leading terms here in the numerator and the denominator, and I can see that the power is the same again. So my horizontal asymptote is the case where I've got the ratio of the coefficients of the numerator and the denominator. So that's all there is to finding horizontal asymptotes. When it gets tricky is when we have to calculate the slant asymptote, which, like I said, we'll see if we have time for. Okay, so this ends part 1 of our lecture for sections 4.1 through 4.2. I hope you took good notes on this and that you're not taking shortcuts, so that you're taking responsibility for learning this material as best that you can.